So as I mentioned, we're going to start playing around with Solver today. On the Canvas site, there should be an Excel sheet. If you don't have it now, go to the Canvas site, download that. I'm going to walk you through it now. Again, based on your preference, if you'd like to do it live, that's helpful. If you want to just sort of watch it and do it after, that's up to you guys. So where the context is there's been a bunch of times, both, one of the first ones we touched is in this multivariate linear free energy relationship. We're talking about a case where we're going to aggregate a whole bunch of data. Once we've got that data, we want to solve or find parameters, numbers, let's say, that allow us to find some sort of correlation. So what you're doing here is you're saying, I measured a whole bunch of things. In this case, the Sigmund data, what he's doing is saying, I predicted my delta delta G, so these are the things that come from DFT. This is my measured data. This is what you actually come from experiment. And what they're doing is they're creating an equation where you get a straight line. So you can imagine that the scoring function you're putting on this is you're saying, I want to aggregate this data in such a way that I get a line with a good R squared. Let's say it's a goodness of fit to a line is what they're aiming at. And what they're doing here is they're saying, I'm going to put a equation together where these values, the NBO value, whatever, those are the actual parameters or the descriptors that they're pulling out from the molecules of interest, whatever is in that actual training set. And then you're going through and saying, I need this coefficient here to be some value I'm solving for. I'm tuning that number bigger or smaller across. In this case, you'd be tuning 1, 2, 3, 4, 5, 6, 7 coefficients. Usually when you do something like this, you bound it. So probably in this case, they're saying you can vary those coefficients anywhere from +2 to -2. And then you're putting it into a program like what we'll show you today in Solver, and basically it's going through and just trying iterations of those numbers. It's very similar to what we saw with Copasi, where they're saying, I have experimental data, you've told me the reactions I can play with, I can go and manipulate or modify my K value, and based on modifying that the K values in the individual point, I'm trying to match my predicted data to my experimental data where there's some sort of an error scoring function they're applying. So the one we're going to do today is a much simpler version of that. This is actually another piece of work that came from my group. We have a constant problem if you imagine doing a measurement. In this case, most of my group does kinetics by HPLC, which means we're measuring concentrations by way of UV extinction coefficients, basically. So what we're saying is, I'm going to run a reaction. I have different time points in that reaction. The reaction is going to give me a sample. That aliquot is being passed on to the HPLC, and then I get a peak on the HPLC. Now the peak is correlated to concentration, but it's not concentration directly, right? This is Beer's law, where we get a signal, and that signal is some absorbance equals, AECL. We're solving for the concentration, but we have to come up with a correlation coefficient that describes how does that peak area directly correlate to your sample. And that might be, you might have to build a calibration curve of the individual sample, different concentrations and looking at response, right? That's an individual point. The downside with doing that is you have to isolate each individual material. You build your calibration curve. It's a whole bunch of extra work. And the other part too is that the way that we do most of our sampling, the correlation coefficient you come up with is not just the absorption coefficient, that's the physical property of the molecule. But if you imagine what you have is, I have a flask sitting on my desk. That flask has the concentration of the reaction I'm running. If I pull a sample from that flask, everything I did in terms of how I pulled the sample, how I diluted it, how I got to the HPLC, how I injected on the HPLC, that's a systematic series of other kind of factors that correlates concentration and reaction to what the HPLC saw. So think of it as its absorption coefficient plus all the physical parameters that are necessary to kind of correlate your response to your sample. So what we decided to do, and this is some work that Maddie Deem did, if we are running a time course reaction, we can start off with an assumption where every species in this chemistry I can observe. So as long as I think that I have a reaction where mass balance is being conserved, then I can say that if I know the total concentration of individual components, I'm going to assume that at any point in time, the concentration of my starting material, my intermediates, my products is equal to a constant. Now again, that's a big hand-waving piece, but we start with that as saying that is a condition that we're going to put in that I can observe all species throughout the course of the reaction. So that's the first one. If I now say mass balance is constant, what I can say is at any single time point, the concentration in the reaction is correlated to that absorbance of individual components by way of my absorbance, the instrument I'm running it on, and all the other physical parameters, which we just call the response factor. So now what I'm saying is that for individual concentrations, I can measure the absorbance. I should get a concentration. What I have to solve for is this response factor. And what I can do, so this is 2 different time courses. If you imagine each snapshot, so let's say a single time point, if I take this individual time point here at this point, I'm going to get an absorption for the blue sample, the red sample, and the green sample. And in order to take that absorption from the HPLC and turn it into concentration, I need to come up with some response factor that converts whatever my measured absorption value is to my concentration. Now, what I have within an individual reaction, so these hollow dots versus the filled dots, those are 2 different experiments of the same materials. So what I can do with this is, in this case, I started with the same concentration of blue, the same concentration of green. Maybe I changed just the catalyst concentration. So the nice thing now is I have 2 different, think of it like a matrices. You have 2 individual different matrices where I have different time course curves, which means I have a linear series of linear sum of equations that says that the absorption coefficient for blue, it's going to be constant for both of those 2 runs. Absorption coefficient for red is constant for 2 runs, and same thing for green. If I had to just take a single time point and say, I've got absorptions, I think I have mass balance, go solve for this response factor, there's nothing, it's not bound, right? I'm trying to solve for the response factor for green, red, and blue using a single data point. Any number for X, Y, and Z would fit for that. But as I start to add individual time points, the same absorption coefficient needs to work, not just for the data series for my blue, my dark filled in ones, and the hollow ones. The same absorption coefficient has to work across each of these, but it also has to work across the entire time series. So what I really have is a whole bunch of individual values where I'm trying to solve for 3 individual coefficients for 2 different time series, where more importantly, the feature, in other words, this time point right here, let's say at the 2-hour time point, has very different concentrations for all the different species, but there must be a common extinction coefficient for my blue, coefficient for the red, and the coefficient for the green. So within the data set, you have a whole bunch of replicate values, but also between data sets, you have a lot of replicate values. So what we're doing here is you go through and use the solver tool to say, I'm going to set up the series of equations based on my data, and I'm going to go through and ask it to go find values for my extinction coefficients for however many species we have, assuming mass balance is constant. That's really the kind of the core piece. So let's jump over to the data set. I gave you guys this Excel sheet. Let me walk you through what this Excel sheet is showing. So we have a reaction. In this case, it's this CN coupling again. We're starting with a dibrominated electrophile at a known initial concentration. We have 2 or more equivalents of my nucleophile, and then I'm making 1 intermediate and 1 product. So it's the mono-substituted material and the di-substituted material. And I can see each of these 4 components. So first off, the assumption I'm going to make is I know at time equals 0 what my initial concentration of this guy is at some value. I know time equals 0 the concentration of this, which means I can assume if mass balance is held, at any point in time, the total sort of electrophile composite is that guy plus that guy plus that guy. That's the total concentration of basically the electrophilic fragment. There's another way to look at it, though, is I can say if I know the initial concentration of my amine, the mass balance with respect to the amine is going to be this plus 2 times this. It's just binning out the stoichiometric coefficients of where that species goes. So first off, I can sort of look at the mass balance with reference to either of my 2 starting materials in this coupling event. I've got a mass balance specifically just for this electrophile, distributed amongst the products and the starting material, and my nucleophile distributed amongst the 2 materials and my products. That's the first. Next, I'm going to go through and I'm going to actually run an experiment. So what I've just quick as a snapshot, what I'm showing you here is this first experiment is a time course series. This is a second time course series. These 2 are replicates of each other. Everything should be same. So the first chunk and the second chunk is just the same experiment, same initial concentrations, just run twice, so that's just a duplicate for a consistency. In this third one here, what I'm doing is I am changing, and I'll just show you in this column here, I'll come back to it. The amine, in this case, I drop. So I'm dropping the amine concentration from 90 millimoles, which is what I'm indicating up here for these two, and I'm dropping it to 60 millimoles. So what I did is I decreased the initial concentration of one of my starting materials. The mass balance with reference to one of those two components is going to be perturbed, but not the other. Then we can do the other component. This case here, this third one, what we actually did is we changed the base concentration. So it has the same initial concentrations as the first and second data series. The only thing that's different is the base, something we can't measure, was changed. So you're getting a different time series based on something that you're not analyzing. Think of it that way, right? Even though I changed the base, I don't have a responding factor because of it, but the time series looks different as a result of that. The last one here, what we're doing is we're keeping the amine concentration at 90. We're dropping the electrophile concentration from 40 to 30. So what I'm giving you here is 1, 2, 3, 4, 5 different time series where we're perturbing the initial concentration of either the electrophile, the nucleophile, something you're not measuring, the base, or a duplicate, where they're exactly the same things where I'm just doing a replicate between the bones. So it's this 5 matrices. In this first column right here, this first chunk of each of them, this is just something else that as a separate, if you do data handling like this in the form of sort of like multiple replicates on Excel sheets, you have to kind of practice through what I would call data hygiene. It's a really good idea if you're doing multiple replicates of things where you're doing these transformations. You have to set up your Excel sheet in such a way where there's kind of a common spacing of where data goes, where your transformed values go, where your math ends up going. So that's why this whole sheet is set up in this kind of a workflow way where I can drop in data into one quadrant and it'll sort of auto-populate the rest of the sheet. So it takes some time if you've never built one of these before. Something I'd encourage you guys to do is after we go through this point, look at how the sheet is laid out. When I worked for Donna, the way she described it was setting up an Excel sheet for doing your data workup is kind of like if you're a samurai, the first thing you have to do is build your own sword. Building your data sheet and how you build your workflow based on your Excel is something you can do that's very personalized. So I'm showing you how I like to do it. If there's another way that makes sense to you, that's totally open, but the real emphasis is you want to try and basically be kind to future you by setting up your data in a way that you can sort of drop in new data and the calculations happen automatically. Otherwise, you're always building new Excel sheets. So in this first column, this is your raw data. These are the time points, and these are the peak areas that I pulled off the HPLC for my amine starting material, the electrophile, the mono, that's the first intermediate, and then the product where it's dye substituted. That's those 4. And then if you go down, it's the same sequence through. Time points, nucleophile, electrophile, intermediate, product, and then again, again, and again. So what's different here is the time series may be different. Definitely the responding variables will be different through it. If you want to take a quick snapshot of it, and again, what I can do is I can grab this, and if I'm just saying I plot it in, I find it useful sometimes to go through and just be able to visualize this and say, okay, well, what am I actually looking at? So dropping a graph on top of it, these are your concentrations, the 2 highest ones. You can see that's your amine and your aryl bromide dropping, and then increasing as your intermediate and then your product through that series. So this is sort of just the raw peak areas of visually what would be coming off the HPLC if you were going to be graphing it in that way. That's the first series. So let's take just this first experiment. I want to walk through the calculations we're doing. So in this part here, what I'm doing is I'm taking the same values, so amine, electrophile, the monosubstituted product, and the actual product. So that's our amine, electrophile, monosubstituted product, and actual product listed out. What each cell is, so if you go in and you click on it, what I'm doing here is I'm taking the raw peak area from the HPLC, for that specific component. So this case, it's the amine from here, and I'm multiplying it by, and I've got this area over here that I'm calling the response factor. And if you notice, this is the $sign, so it's a referenced value. What I'm saying is every one of those time points for my amine, I'm multiplying by a constant. So I go down this line, I'm saying that This concentration of amine here would be calculated by taking the peak area from that time point multiplied by that extinction coefficient, or the correlation factor. And I do the same thing the entire way through, where I'm taking just the indexed time point and I'm multiplying by that same cell that we had up over here. Because what I'm assuming is the extinction coefficient isn't changing through the course of the reaction. The amine value is here. So having them set all to 1 like this is effectively saying that the concentrations that I have on HPLC is a 1-to-1 correlation to what I'm actually getting for real concentrations. This is not true yet. I'm just putting in a populated value of the value equals 1. When it's sitting that way, each one of these things I've set up where I have sort of a visualization, a plot. In this plot at the end of each one, right now with the value that's set equal to 1, this is equivalent to what you'd see off of the HPLC. Now the one thing that you've got on this graph, if you track it through, that's my starting material going down. Orange is the other starting material going down. They're all listed out here. The one thing that's new from that first graph I showed you is this value here, what I call the mass balance. That's this green one right here. That is being generated by going back to my concentrations. This is what I'm trying to calculate right now. I've gone through and I've just got each of these cells is the raw peak area from the corresponding component multiplied by the extinction coefficient of those 4 components. So in other words, amine here is being multiplied by the amine coefficient, the starting material electrophile by the starting material electrophile, the mono by the mono, and product by product. And again, these are global values we're going to use for the entire sheet. So I take those concentrations, and then what I have here is a mass balance, and you see I have 2 different mass balance calculations. I'm saying mass balance here, this is in reference to the electrophile, and what I'm doing here is saying, if you go light that up, I'm calculating the mass balance with respect to the electrophile by taking my electrophile, my mono, and my product, and I'm just adding them 1 to 1 to 1. So I'm saying as long as those concentrations are constant and as long as my extinction coefficient is correct, I should be able to sum those 3 values, whatever the prospective concentration is, and I get what I think the total mass balance is. And I do that for each of the values going through this sequence here to show what is the mass balance with reference to my electrophile. The amine, I do the same thing, slightly different equation. Now what I'm doing with the amine is I'm saying it's the amine, the monoproduct, and since the product has 2 equivalents of the amine, I'm saying it's twice that concentration. I'm counting it, I'm doubling it up. You could do the same thing by half, 1, but either way, what I'm doing is a stoichiometric solution to the overall mass balance in the system. And then again, what I'm doing is I'm taking that concentration or that mass balance and I'm running it the entire series. So as time evolves, if those concentration values are incorrect, the mass balance is going to wobble basically. This theoretical value here, that's the initial concentration of whatever the species I'm focusing on. So here, since this is relative to the electrophile, my theoretical mass balance at time equals 0, I only had this material, so I'm saying it's 40 millimoles. And for the amine, the theoretical mass balance, I started off with 90 millimoles, so that's my theoretical mass balance there. Now, I'll come back to this error value here, but if you look at this, this is my time series. This green dots right here, that's tracking mass balance over time. Based on what you see there, what would you conclude? So what, in your own words, are you seeing when it says, okay, I am plotting mass balance over time, where right now I've set all my extinction coefficients to equals to 1. What does it look like? Is it constant? And again, if you had to sort of just describe it, it looks like the mass balance approaches a constant value later in the point, and it's really off initially. Now remember, as you walk through this time series, the difference in this part right here, early in the reaction, it's composed of more of my nucleophile electrophile, my amine and my aryl bromide. Later, it's composed mostly of single product. So that makes sense because all I have over here is a single product. I got nothing else. That's why it looks constant. Over here, it's off because I have some random values for my extinction coefficients. This is not a true reflection of the concentration in the system. That's really all we're saying. That's the first part. Okay, now that we've got this, what I can do is if I've defined what the theoretical mass balance is, this is the true mass balance. You see, I'm supposed to be accounting for 40 millimoles, and based on the values of equal to 1, I'm only accounting for about 0.5. So I'm way, way, way underreporting what the concentration is. I'm missing a lot of mass in this case. That's what this value is here. This is the error, and what I'm saying is I just want to take what I should have, what I actually have as a difference, and then I'm just squaring it. So this is kind of like your r-squared value. The reason I'm multiplying it, I'm squaring it, is because two things. By squaring that difference, I'm making every value positive. I don't have a positive or negative error. It's always going to be a positive value, so I don't care if I'm high or low. Error is just error. The second thing I'm doing is by squaring it, you're taking small values and you're really cranking up the dial. Basically, think of it like a sensitivity. You could just take an absolute value of differences, but by squaring it, you're saying, look, the closer you get to the right value, the more I'm giving you a big cookie, right? Basically, you're really cranking the knob on it and saying, I'm rewarding close values more than these far away ones, which will just blow up your error. So now that I have that, I have an error associated with every single time point. And all I'm doing right here is summing this entire column. So all I'm doing there is saying, for this data series, the sum of the error is all of these values stacked together to get a single value, right? So what I've done now, I have a single data series. I have a single data series I measured. I have some math that I'm doing that correlates these measured values to the concentrations I'm hoping for. I have 4 unknown values I'm trying to find, and I have a scoring function. In this case, it's what it should be minus what it is. Sum up all those errors to give me a total negative value. So if you had to sort of describe this, the exercise I want to do now is I want to play with these 4 numbers. I want to make them bigger, smaller, whatever. As I do that, I want to watch my error value. I'm just pointing at this one value here, and I want that as small as possible. Right? I want to try and minimize this value here. So you could do this manually the way the sheet is hooked up. I can go in here to my aryl bromide and say, okay, I'm going to make it equal to 50. What did that do? Well, my mass balance got a heck of a lot worse. It's way off now. I'm over-reporting here, and I'm under. So you could go through and manually try values for this until you eventually get closer. Worst video game in the world. Not something that I recommend doing. What you can't, like the way Solver works is now that the system is set up, you have what we would call a cost function. We have a way of scoring the output. In this case, it's our error value. And we have things we want to manipulate. I have 4 values I want to change. So under Tools, there should be this little guy here called Solver. When you open up Solver, you're going to get a window that looks like this. Now, again, if you... This is where both language models, online YouTube tutorials, there's a ton of other ways of sort of talking about how to use a tool like this. So if there's other ways that you want to apply it, definitely go and check out that kind of component. What I'm doing here is, normally when you bring it up, if you've not entered anything, it'll look just like this. You have your objective. This is what you are pointing the tool at and saying, that's the thing that I want you to interact with. In this case, my objective is, let's say it's this value here. It's just this sum of my errors. So I'm saying focus on that value. What I want you to do to that value, I want you to minimize that value. I want you to make this error as small as possible. And then down here, how do you want me to accomplish that? Well, I'm going to let you click on this down arrow, you select your range, and I'm saying you are allowed to change those 4 values in any way you want such that this error gets small. That's the simplest one you can do for now. I'm not bounding it in any way. I'm not saying it has to be high or low. I'm just saying play around with those 4 values to minimize that target value. And I'm just pointing it right now at this single value, right? So give that a shot first. When you're done, you should just be able to push solve, and it will go through something. Usually it'll pop up a window down here, and it says, okay, I did something. Do you like these values? If you look, it's changed these values here. It used to be 1, 1, 1, 1. Sorry, here, I'm going to say OK and hold them. But it used to be 1, 1, 1, 1. It's gone through the numbers and it said, OK, 74.9, 52.7, 51.1. Those are it scanned through those points and did it. Now again, depending on bigger sets, if you go down, one of the other features you can bring in, this is kind of like in Copasi, the kind of optimizer you use, there's things like gradient descent, evolutionary programming, all those things is different parameters for guessing numbers. So for a simple one like this, it really doesn't matter which one you use, but if you go to higher convolutions, you may need to use a different kind of optimizing optimizing algorithm, but most of the time, the default will work fine for simple sets. The only other one I want to mention about that as well, in this case, I have no constraints. I'm saying you can choose any number you want, positive, negative, big, small. In that other box down below when you're setting up your solver, that's where you can put in things like, I want you to find these values, but value 2 and value 3 must sum to this final value. Or you're not allowed to go over this other one. That might be something if you're trying to figure out, let's say, an equilibrium constant. If you know the pH value of your system, that's another piece of data, you could then bound your total solver value to some other piece of data, which then gives you sort of other math. So you can get pretty creative about linking some experimental data with some other circumstantial data. Maybe you know the pKa of the base that you're dealing with, and you'd be putting it into here as a constraint or something like that. So give that a shot first. Can everybody give me a thumbs up if you're doing it live that actually worked? Sick. All right. Congratulations. Now, look at this. It changed these 3 values. It didn't touch the amine. Why? In your own words, why does that make sense? Yeah. Exactly. This mass balance error, all we're saying is your only point of light is make that sum of the error super small. That error is only calculated by the theoretical mass balance of your electrophile. It doesn't have any idea what's going on with the amine, so it didn't touch that value. Messing around with the amine gave it no reward, so it doesn't touch it. Okay, so that's good. We've got good values for 3 of the 4. How do you propose, based on what we've got here, how do I get the amine value? What might I do? Yep.
Just run again with the amine target cell.
Okay, so we could go back. You could say tools, solver. Instead of now, see the objective, we were pointing at this value. We could say, actually, I want you to say that value is the one I want. You're still trying these 4 values. We're not changing the target. Say solve. Whoops, sorry. Objective is here. Solve. Bang. It now found a value for this one, touched these ones over here. Now again, in that case, remember the aryl bromide value is not the thing it's going to be messing with. So if you suddenly saw that value jump or change, maybe it just threw a dice on it and was like, well, I can make this anything I want. So it is something you might want to watch for in that case. But there, that looks pretty good. Just as a quick point here, these 4 values, those are the actual correlation coefficients that we've measured independently from HPLC. So this is just as a quick reference. These 4 values in the ABS are, if I had to do this experimentally, this is what I would have calculated using a traditional concentration curve. I'm changing the concentration of the thing I'm measuring, and I'm doing my full analytical workflow. So that ain't half bad, right? 100, 100, 74, 73, 53, 57, 53, 51, right? Not too bad. So that's confidence that, hey, the method I applied actually has value here. But if you look at the things, where does it have the biggest problem? Like, where's the biggest differential? Yeah.
The biggest issues are the intermediate and the product.
Yeah, these 2. Now, then to say it sort of like quickly, what we have here, how this is working, and if you actually look at the whole curve, you see how our green line here, that's the new mass balance in the system. You see it's pretty constant. There's a little bit of a wobble in it, right? It goes a little higher and a little lower, but it's doing a pretty good job floating around that value of 40 because that's what we asked it to kind of do. The concentrations, if this is now millimolar, we started at 90 and we do have 90. We started at 40 and we do kind of have 40. Everything else matches in. One of the ways to think about why those intermediates are farthest off, what's happening, right, is we're basically taking, think of it as a snapshot of each one of these time points. I'm trying to find a value for my blue, my orange, light blue, what the numerical coefficient of those guys are. And I'm trying to say that if I find that value, that constant works for every other value in the system. If you look at time points like here, where you have equal amounts of like product and intermediate, those are cases where you're trying to determine 2 values with a single data set, basically. You know, if you have this highest degree of overlap, what we're saying is there's actually a whole bunch of different values for your intermediate and your product that probably will give you pretty good fit, because what I could do is decrease my product value and correspondingly increase my intermediate value, and it might compensate for each other. right? This is kind of like two unknowns with one effective data set because they're correlated to each other, because you could define the concentration of your product in terms of your intermediate and intermediate in terms of the product either way, right? So they're coupled. This is where a single data set is probably not enough to lock it up, right? This is where if I have just this one time course, I should not just go through and focus on this sum value here. More importantly, I shouldn't have to go through and say, well, I'll do an optimization here and then I'll go do an optimization here. You could actually create a new value, which is just, call it sum of amine and electrophile. And I'm going to say that equals this plus this, right? So now I have a new value where I'm saying, look, it's not just the error of the one, it's not just the error of the other. You need to actually make this sum of those two errors the best. And again, you can do it this way where we're creating an actual value. I can go through now and say, I want to use solver. And I'm now going to target this value, my aggregate of my two sums. Say, that's what you have to solve. You're still messing around with the same values. Go and solve it. And now it's going to tighten it up a bit more. See, it dropped from about 41 to about 36. If you, yep, these look good. If you go up here, we've kind of tightened up a bit more. We're still in that range where these two are pretty good. These two are kind of about equal. It's kind of ranking them about the same for those two. And meanwhile, there's actually a real slightly difference of that intermediate. Again, that's better in terms of a single data point or a single push. One other thing I want to focus on, though, is you can actually go through in solver here. Instead of saying the objective is just a single value, the other way you could do this is say the objective is that plus, oops, I think I can, can't I? No, I can't, single value. So I thought there was a way. Yeah, there you go. That plus this. Plus. It has to be sheet. This is the much harder way. Sheet 1, numerical reference, and whatever that one is. That's S. $14. Solve. Oh. Really? Okay, screw that. No, you can't under this version. You used to be able to actually define your objective as an equation. So it's not playing nicely there. So that's why I use the other way. What I mean is, that's why having this value here as a sum of these two other ones, you're reducing it back to a single value or single cell that you can point solver at. So if you want to do other math, like there used to be a way where in the solver one you could actually define the whole equation. Looks like the version now, it just requires you to do the equation on the Excel sheet. So in this case, if I want both the two values to be considered, I have to say that error plus this error equals my sum of my two errors, and then I point the Excel value or the solver value against this, so that we're multiplying against all these against now the aggregate sum. That's one point. Now, what we just did is we did a solution solver for a single experiment. And remember, there is actually an error value for every one of these replicates. So this is the mass balance error for that replicate value, both in terms of the electrophile and the amine. This is the one for the reduced amine value. So we have a different initial concentration of the amine. Down here, this is the different base value. So each of these not only is it a replicate, so you're getting experimental error being considered, but you're also starting with initial concentrations and even time courses that have different time representations. In other words, doing the solution considering all these values will give you a way better true answer because you're coming up with a single value for extinction coefficient that has to fit every one of your data sets in every one of your different permutations. So that's what this up here is for. These columns up here is the total sum of the mass balance for my electrophile for all 5 data sets. So what I'm doing is I'm just summing up the electrophile error from experiment 1, electrophile error from experiment 2, 3, 4, and 5. That gives me my aggregate sum against all experiments. and then this is my aggregate sum of electrophile experiments together. So this is where if I now go back into Tools, Solver, I'm going to point the solver at this value, solve. What is wrong with that value? That looks weird. Boink. What you're getting now is an absolute value relative to this one across all 5 experiments. And you can see now, by doing that, we're getting really close to our experimental ones. More importantly, we've properly differentiated between this small variation for my 2 different points. And again, that's only possible because in the 5 data sets I have, not only is it replicates, which gives error in a single time point has been helped to be normalized out, but I have other experiments in here where both the time course curve at same concentrations is different, and my initial concentration of my electrophile is also different. So that's kind of like back to this example here. If you can get something that looks like this, where you have 2 of the same runs, 3 of the same components represented with that, but very different time representations, you will get the best quality data because you're getting a really good representation of what the individual value should be. It's your highest determined set, basically, for how you're doing your linear regression. So that's just, and you can go through and do the same thing. I could point it at just my mean error, or I could modify this value here and say, no, I actually want to say it's this value. I want this equation to be the sum of both of the 2. So I actually want it to be that plus that. So now this is not just the sum amongst all experiments for my electrophile, nucleophile, this is the electrophile and nucleophile. If we go through and ask it to point at that value, that should be probably the best of all of them, hopefully. Bloop. Tightens up a little bit more, and again, there's just a small perturbation across that. Just like we've done before with, what do you call it? This is still a random number. Like what we're doing is each iteration, you will get a little bit of perturbation in the numbers. If you run this multiple times, what you'll see is that the absolute values of them may wobble around a little bit. That's just coming down to whatever the error in your data set is. You may actually have, think of it like a buffering effect. The mean value may wander between 1.01 and 98 for any individual run. So one thing you can do is multiple sort of initiations of your solver, solve those, or like record the values for individual starts, aggregate those all together, and create a Gaussian distribution of the real number. So almost what you're doing is you're saying, I am running an experiment. One time of me pushing, find solver creates these numbers. If I don't change my target and I just run it multiple times, what you'll see is the absolute values of these will wander around by a little bit. By recording each of those initiations, you can actually do a statistical distribution of saying, you know what, for this particular data series, I get values from solver that wander between 1.02 and 95. And that's just because of the data set that I have and the error in that data set. All those values are about equally as effective. You can actually go through, and if you run them enough times, you can create a histogram where this becomes like a Galton plot. You know what I mean by that? Galton board. This is how we know things that have random distributions fall in sort of a Gaussian distribution, like coin flips, basically. Well, that's only 2. It doesn't work that way. If you take this, if you look it up on Amazon, this is always one of those stupid fidget toys I wish I got. You can actually get this this object where there's a whole ton of small steel balls, little tiny sort of what are they called? Well, steel balls. Little marbles, basically. And they all funnel through this single point where what you have is like a Plinko board, individual pegs that's distributed amongst here. What you're doing in this physical setup is I'm dropping beads through this point. Each time it hits one of these, you have a 50-50 chance of going either way, random distribution. If you actually just let this thing fall out, at the bottom, what you'll get is bins. Where does it end up? And with enough beads, you'll get a perfect Gaussian distribution, which is just representing the physical, like if I have a 50-50 choice split this many different times, I will have a statistical binning of how many different values I actually get. This is basically the physical version of what any normal distribution by Gaussian looks like. You can do the same thing with these values, where if you run it enough times, you can basically create a histogram of how many times did I get a value for my amine of 98. That becomes your center point, that's your mean average, and you can actually say that for my data series, I can define this with an error bar of what my fit value actually becomes as well too. So that's the quick part here. Does anybody have any questions about how this sheet was built or how you would use it? Yeah.
More just like a question, is there a reason why you would sum all the errors and not do any other function like multiply?
Anything you want, right? Like this is where what we're getting into this is, in order for this to work, what you need is, first of all, your data. That's what you measured. You have to have an objective. I'm looking for my concentrations. You need something I'm changing, a knob or a value that allows me to manipulate like what is right and what is wrong. That's the variable or the experiment you're doing. And you need a score. You need to say, how close am I to the thing I'm looking for? Honestly, that narrative on its own is I found this really difficult when you start playing data science, because I need to be able to take a reaction and say, well, what am I looking for? A good reaction. How does good fit into this Excel sheet, right? The terminology we have of like, this reaction is good, we have to featureize it as something that's numerical, so maybe high yield, maybe cheap starting materials, maybe short time. But then once you've got that visibility to say, I have a way of scoring this, in this case, this is just an R squared against what I think I'm looking for. It's a fit to this mass balance. But you can use any other error function that makes sense for you, right? In this case, I'm starting with the assumption that mass balance must be constant. And this is where this technique breaks, is if I had an experiment, like if you look at this, so for anybody else who's done sort of like palladium couplings, does anybody have an idea of why mass balance for this reaction might not be constant? What's a byproduct, very common byproduct you get from like palladium cross couplings like this? Well, palladium black is catalyst death. Remember, what I'm worried about is I'm saying that I can observe all mass relative to those two starting materials. What if I debrominate my starting material, right? If I just do dehalogenation, where I don't make either of those two products, I'm not making any cross coupling, I didn't measure that. That's a bucket of reaction that I did not observe and I didn't quantify. Anytime in this case, the major ones I would worry about is probably debromination of my starting material, maybe oxidation, or like these are, who's ever played with electron-rich anilines, they're horrible molecules. They just turn to, you look at them wrong and they turn to polymer death and stuff like this, right? So there's a whole bunch of things where those two starting materials may go to something that I can't measure. It's polymer, it's dropping out of the reaction, whatever. So that's where this method falls apart, is if I can't measure all my starting material in every product, this will not help you. The way around it is either analytically look harder, or what you can do is see what I've done here. I assume that my mass balance is constant through the entire reaction. If I know that I'm losing starting material at a zero order rate, I can actually modify my mass balance as a line. I could say that I know that linearly over time, my mass balance is falling off according to a straight line, because I'm assuming I'm losing starting material at a zero order process. So you can actually tip that angle and still make this work, but you've got to make a call at where is it going and how fast is it going there, right? The other one that we've used sometimes too is I can create sort of a dummy profile. I can probably set you guys up one if you're interested to see this. But if you have sort of something where the mass balance rapidly dips late in the reaction and I have no explainable reason why, then I know I'm looking for something that showed up at that time point. So either analytically I go back and try to find it, or I create a data series that says, look, something has to be there. I don't know what it is, but I'm basically putting a filler in place for that component. It becomes like a dark matter kind of explanation at that case. Any other questions on this? So I'm going to give you guys an assignment for a couple of the reactions where I want to use you guys to play and use this too. Honestly, this is one of those things we're spending a bit of time with this. Not only will it up your Excel skills a little bit, which can be really, really helpful, this is one of those things that's dug me out of more problems if you can sort of use this as a way of sort of digging through your data. And again, the big practice or discipline of this is setting up your data sheets in such a way that you can use them reliably for many different data treatments, right? So this is kind of like forging, if it's something that you do repeatedly, forging this in a way that you can use for whatever your experimental treatment is very, very useful. All right, I will see you guys on Friday.